One of the things that we tend to forget is that springs store energy. And so when we ever have a problem that has springs in it, we tend to forget how in which they store energy and how it's related to simple harmonic motion. Now, we don't have simple harmonic motion on our exam now, and I'm a little disappointed by that, but not terribly disappointed. What I'm disappointed about is that they could easily ask us questions that remind us about things that we have to deal with when it comes to springs that we're not prepared for. And, you tend to think that, well, if there's no simple harmonic motion, then there's not going to be any springs. But, springs store energy. And because they store energy, we often have to deal with their energy storage potential. So here we go. I'm going to drop a box on a spring, of spring constant K, and the box has a mass of M and is located a distance of, let's go with H above the spring. Now there's a lot of questions I can ask here, but there are two questions that students often overlook. Look, if the box sticks to the spring, it could definitely bounce up and down on the spring. And I want to talk about that question, in more detail, even though it's not going to be on the exam. On the other hand, there are two questions that students often fail at, and they are, what is the maximum compression of the spring? And what is the maximum speed of the box? And students often make a huge error in both of these questions because they are very different. So there's the max compression. That's an energy question. Let me just say it right now. This is energy. But there's also the max speed of the box, which is a force question. Now, this goes against a lot of what we've talked about over the course of the year because many of us, and me included, have emphasized that speed is all about energy. And that's not wrong. The problem here is that the maximum speed of the box isn't about energy. It's about acceleration. The maximum compression of the spring is definitely about energy because the spring is going to absorb the energy. Therefore, we know that when the box contacts the spring is going to begin to compress some distance x, and eventually the box will come to rest against the spring. Now, if we were to consider the energy of that circumstance, just the energy, then the total height change of the box is going to be h plus x. So the box has gravitational potential energy when it's released, and that gravitational potential energy is totally based on the maximum change in height of the box, which is h plus x. At the other end of this spectrum, the box now is stopped. So at the top, it has no kinetic energy. At the bottom, it has no kinetic energy. So again, we have potential energy, and this time it's elastic potential energy. But elastic potential energy is only based on how far the spring is compressed, because now we've done work against the spring to compress it. So students throw in things like kinetic energy here and all sorts of stuff, but none of that matters. The biggest problem they have is recognizing that the absolute change in height is mg h plus x. And that has to be equivalent to now how much the spring has been compressed. And once we recognize that, we have a relationship where we can figure out how far the spring is compressed compared to how high the box was, all that kind of stuff. There's nothing particularly interesting here. Now, again, I want to save that because when we talk about this tomorrow, there are some things here that are important. But the maximum speed of the box is where students really screw this up. Because a lot of students think that the box has reached its maximum speed the moment the box has touched the spring. And that can't be farther from the truth. They think that because when the box touches the spring, it begins to compress the spring, and its energy is changing from kinetic to potential. And that's definitely true, but that doesn't mean that the box isn't still acquiring more kinetic. It has more potential. When the box touches the spring, it has more gravitational potential still. It's going to need to convert that either to kinetic or elastic potential. The thing about the box touching the spring that's important, and here I need to pause for a second. Okay, so when we look at these three different states of the problem, at the beginning, we know that the first box has gravitational potential energy. Sure it does. But there's the gravitational potential energy with respect to the top of the spring, but there's the gravitational potential energy with respect to the lowest point it will achieve. Those aren't the same. It's definitely going to compress the spring. So the box falls, whatever this distance is, we'll call it h, and then contacts the spring. But at this moment right here, it still has gravitational potential energy because it's above the lowest place it will make it. And it still has kinetic energy. That's true. Now, there's this last point over here. This one's easy to see because this is the point where it will only have spring energy. It will have compressed to the lowest point. It will have no gravitational potential energy because it has compressed the spring some distance x and it's no longer moving, so it has no kinetic energy. But there will be this middle place right here. And this is what students forget. This middle place will still have gravitational potential energy. The box is still moving. It's going to have kinetic energy, but at this moment, it's no longer speeding up. It's slowing down. But it also has compressed the spring a little bit, so there's some energy in the spring. So some of you are asking, well, what do you mean it was speeding up? Well, when it first touched the spring, that instant it touched the spring, the net force on the box was just mg. The spring wasn't compressed yet. So it's barely touching it. There was no normal force. There was no Hooke's law force. Now, I agree. The instant later, there is a small normal force, which would be equal to kx. But it's not enough yet to slow the box down. The weight of the box will be greater than the upward force of the spring, and therefore the box will continue to accelerate downwards. Here's where you all make mistakes. The box's final maximum speed isn't related to energy. The box's final maximum speed is related to the net force because it will continue to accelerate until the net force equals 0. That's the break point. Remember, changes in velocity are about force. So when the net force equals 0, at that instant, that moment, the acceleration will be 0. If the box continues to move downwards, then there will be a point past here where the upward force, kx, will be greater than mg. And now the box will be slowed by the upward force of the spring. So the acceleration has to slow the box. The upward force of the spring has to slow the box. And I can't believe I wrote kg there. That's because it's late and I'm trying to do this. That will be kx. That's right, kx upwards, mg downwards. So the maximum speed of the box will be when the net force is 0. And the net force is 0 when kx minus mg equals 0. So what this does is this gives us the value of x, how far the box will have to push against the spring until the net force equals 0. So I'm going to write this as x, how about naught? Who cares? Because that's going to be how far the spring is compressed until the box is at maximum velocity. And that'll be mg over k. Now we still don't know what the maximum velocity is, but we know that this is the energy of the system when it's at the maximum velocity. And this mg, how do you write this? I guess h plus x naught is how much energy the system has when it is above the spring and just been released with respect to when it will be at maximum velocity. Now, there's a couple things about this that are tough to deal with. First, if I choose x naught to be my measurement for where the maximum velocity is, then that is x naught. And if I choose that to be x naught, then at that instant I'm saying that the gravitational potential energy is 0 with respect to this location. And I'm going to get a slew of questions about this tomorrow, but remember, gravitational potential energy is always with respect to the lowest point of your choice in the problem. So if I choose the lowest point to be maximum velocity, then I can state that at that instant, the gravitational potential energy is 0. And that's what I'm going to do. So by doing that, I get to say that mg h plus x naught equals 1/2 mv squared plus 1/2 k x naught squared. And now your job is just to find the velocity. You're solving for v. Now this is actually v max. It will be the fastest velocity of the block relative to its drop from that height. So that's algebra. I'm going to leave that to you because, quite frankly, I'm doing this at 10 o'clock tonight and I don't really want to do any more. So there you go. You guys figure out what the maximum velocity of the block is, and you remember that this is a spring question. Doesn't matter that there's no simple harmonic motion. You are still going to get spring questions on the exam. Tomorrow, we're going to take a look at simple harmonic motion, or at least we're going to take a look at second order differential equations, which are related to simple harmonic motion. So you enjoy. Good night.